We will begin our session that is the third and last, but certainly not least, keynote speech that we have in Open Science Fair. It is a great pleasure and privilege to introduce John P.A. Ioannidis, whose most, for me, the most important element of his CV is his name, because those that know Greek know that John is Yannis, is the Englishized version of Yannis, so we have exactly the same first and exactly the same last name. The middle names we can differ, but that's details. So everything else that he has achieved is, details. John Ioannidis is the most important thing. And you'll have the Ioannidis and Ioannidis show at the end after his speech. So I will be extremely brief, given the size of his CV. And some of these things I have to read because it's impossible to remember. Okay, he is a professor at Stanford University. And according to Atlantic Monthly, he may be one of the most influential researchers alive right now on Earth. He has appointments in very many departments at Stanford University. He's the Renborg Chair in Disease Prevention, Professor of Medicine, Professor of Health Research and Policy, and by courtesy, Professor of Biomedical Data Science, Professor of Statistics, Co-Director of Meta Research Innovation Center at Stanford again, and Director of the PhD program in Epidemiology and Clinical Research. He has received tremendous number of awards, many recognitions. He has honorary doctorates from many places, including my university, the National and Kapodistrian University of Athens. And he has written some of the most influential papers that are shaking the way we do science. Some of his papers have received more than 20,000 citations. And all in all, he has, because by the minute it changes. Well, as of 2 minutes ago, it was 140,000 citations in his papers. It is, if you have a few thousand, you're happy with your life. He has 140,000. That's the kind of influence that John Ioannidis has had on science. And reproducibility, and he has proven that most medical science publications, medical research publications, are wrong. And it's not about, an algorithm of some esoteric thing in some computer that is wrong. It is medical research that affects all our lives. And the shakeup that the scientific community has had because of John is major. Reproducible science is the right science, and as we claim, open science is one of the main avenues to go to reproducible science. So John will talk to us about changing research practices towards reproducible research. John, it's a privilege.
Thank you for this great invitation. I'm really honored to participate in the Open Science Fair, especially since it's happening in Athens. It's the first time that I'm giving a talk in this beautiful building, which is really astonishing. And I hope that next time there will also be books in the bookcases. So you heard one example of reproducibility from Yannis. Our name is reproducible. And I will try to talk about some more examples of reproducible science and how we can change the way that we do science to get more reproducible results. Do we have a crisis? Some fields are thinking that we have a reproducibility crisis. And one such field is psychology, where no one was doing any reproducibility checks until recently, but then at some point, 270 top psychologists and their teams took 100 papers from their creme de la creme 3 top journals, and they tried to repeat the very same study again. Regardless of how you read the results, about 2 out of 3 of these creme de la creme studies could not be reproduced. Not really what the field thought, and that's an occasion for some soul-searching. What is going on here? What is wrong? Is there anything wrong? Is it seriously wrong? How are we running research? How are we running our science? How are we disseminating our science? There's also debate about how much of a problem there is, and I call that the reproducibility wars. A few months ago, eLife started publishing the reproducibility results for cancer biology experiments. Again, the most highly cited papers in the field being repeated by independent teams to try to see if they can get the same results. Different conclusions, but roughly only 1 out of the 5 could be strictly reproduced. 1, maybe, and the other 3, not really. Again, do we have a problem? How big is the problem? Are we having lots of sloppy science out there? And what exactly is sloppy science? Is it fraud? I would argue that science doesn't really have a big fraud problem. To become a scientist, one needs to work very hard, go through many, many years of training, and eventually not get really a very high salary. So, why not become a politician or something else that would give him an advantage very quickly and spend 10, 20, 30, 40 years, a whole life in science? Surveys suggest that fraud is not the problem. What seems to be the problem is questionable research practices, suboptimal science, maybe a little bit of sloppiness. Sloppiness could be due to ignorance. It could be also due to intention to try to get something. And we all want to get something. That's why we are in research. We want to deliver something that is interesting, valuable, has utility, can change the world, can offer some benefit. So it's easy to fool ourselves by cutting corners, by being a little bit sloppy to get a little bit more interesting results. And in some modeling study that I've done with David Grimes, we see that with some assumptions where we simulate a universe of scientists, some of them diligent, others sloppy, and some others completely fraudulent, in the current environment, sloppy scientists have an advantage. Over time, their generations will turn out multiplying at a faster rate compared to scientists who pay extra resources, extra effort to try to validate whatever they do. Because they end up being slower, at least within their team. What is reproducibility? Everybody's talking about it. This is a survey that we published about a year ago where we asked across 22 different disciplines of science how often people mention reproducibility of results or something similar. Exponentially growing mention of these terms, but actually what is it that people think about when they mention these terms? They mean very different things. And basically they think of 3 major groups of reproducibility. Reproducibility of methods, of results, and of conclusions. These are very different. Reproducibility of methods pertains to having some software, having some script, some code, applying that script on that software, and getting the same result. For computer scientists, for informatics, this seems to be very straightforward. If you don't get the same result, then we are in trouble. Do we have a problem of reproducibility of methods? Yes, we do, because very often these software and scripts are not available. Or seemingly they're available, or there is some policy trying to make them available, but the policy is not adhered to. So you click on a link, supposedly the data, the software, and the script should be there, but it's not. And then you cannot really tell whether this is reproducible or not. Reproducibility of results means that someone is running a new study from scratch. New experiments, new observations, new people, new participants, new data, trying faithfully to come as closely to the original result. Do we get the same result? Very often we don't. That's a failure at the level of reproducibility of results, or replication. That's another widely used term. And finally, reproducibility of inferences means that, I don't know, maybe we have 200 people in this room. If I were to give you the same data with the same software, the same script, the same analysis, the same results, the same written report, and I let you read them for a few hours or even a few days or even a few months, and then I ask you, so what do you conclude about that? You may conclude different things. Your inferences about what that means, let alone whether something is to be done about it. And in medicine, for example, in health sciences, this is very crucial. It's not just curiosity. Do we need to give this treatment? Do we need to go ahead with that intervention? Should we give another intervention? This is really critical. People will not agree. Reading the very same data, the very same package of science, they reach different conclusions for various other reasons that depend on their priors, on their beliefs, on the theories that they adhere to, how they understand the rest of the literature, and so forth. There's differences across fields in reproducibility. So any culture of open science cannot really work unless it takes into account what each field wants to achieve and what are acceptable norms in the field. Some of these norms may just be off. They may be wrong, they may be suboptimal, they may clearly need to be improved. But even when we try to make everything perfect, there will still be differences in all of these factors that I list here. There's differences in the level of determinism, in the level of what we call success, based on what rules, based on what statistics, how stringent are the thresholds that we use, how much heterogeneity that we tolerate, and how much diversity in our experiments, what are the typical methods that we use to try to get the results and report them, how much of a closeness of fit to the hypothesis makes us happy versus leaves us with skepticism, and eventually also what kind of a difference does it make, this result versus a different result? Is it just curiosity and scientific peculiarity, or are there going to be consequences about people being harmed or conversely getting a larger benefit? This is a map of science that my colleagues at SciTech, with whom I collaborate, have drawn, looking at 20 million papers and 200,000 patents over 16 years. There's 2 million patents. There's about 200,000 clusters of different disciplines, and the different colors pertain to major disciplines like chemistry and medicine and physics and computer science. Each one of these clusters has a life on its own. It has its own rules of engagement, its own openness or closeness, its own research practices. They all use the scientific method. But in some of these fields, it's very easy to publish a paper that uses a particular statistical method, and if you use the same statistical method in a neighborhood field, it's not going to be acceptable. In one field, it may be fine not to replicate, and then you move a little bit further, and in a neighborhood field, you have to replicate before someone will consider accepting your work. So these fields do have some communication, but they also have differences in the way that they define reproducibility, openness, how research practices are applied, and what do we seek out of applying the scientific method. One common denominator for almost all scientific fields is that all scientific fields, eventually what they publish seems to be significant. In medicine, health sciences in particular, this means that almost everything is statistically significant. Looking at all the biomedical literature indexed in PubMed since 1990, and close to 1 million full-text articles as well, by text mining we found that whenever there's p-values reported, 96% of the time, they report statistically significant p-values. So using that rule of thumb, which is very prevalent across life sciences and many other fields, leads to a very boring success rate of close to 100%. Discovery becomes very boring. Passing that threshold means nothing. It has no discriminating ability compared to the ability to discriminate what might be more likely to be correct versus what might be more likely to be null in the times of R.A. Fisher, who started discussing p-values as an illustration rather than an absolute rule. This is the typical recipe of research practices. This is what most fields tend to accept as the norm. Usually you have a single investigator who works alone, and therefore he or she has to be competitive. Unavoidably, most studies are going to be small because resources are very limited. Trying to be successful, the p-value threshold chosen would be just a p-value of less than 0.05, and that would be claimed to be a success. trying to be always successful, one will do a lot of post hoc analysis, cherry pick hypotheses, cherry pick results that highlight the most prominent ones, but not necessarily the most correct ones. No registration of the hypotheses or the protocols that are being assessed. No data sharing of all that effort, because that offers competitive advantages to other scientists who are working in the same field, and how is that scientist going to survive if they share their weapons? And no replication, because replication is seen either as a Me Too type of engagement or as an opportunity to show that what you have discovered is not really so, and then you're back to square zero after doing double the effort. So no incentives and no rewards really for sharing, for openness, and for reproducibility. When one works in that type of an environment with such an incentive structure, we tend to get tons of very small studies. And this is looking at 1,800 studies roughly of fMRI in terms of identifying foci in the brain that are related to specific activities or psychological features or diseases. The main way to be very successful, to get a lot of loci, a lot of foci light up in these studies, is to perform very small ones. If one starts performing larger studies, most of these foci go away. And most of that literature is still operating in very, very small sample sizes. I guess that if we were to exceed the sample sizes that are shown here, the vast majority of these signals are likely to go away, and in many conditions, maybe none would survive. This is not just a problem in fMRI. It's something that we see across much larger disciplines. In this paper that we published 4 years ago, we looked across very different disciplines in neuroscience, spanning all the spectrum from cell culture work, animal experiments, preclinical work, and clinical trials. The common denominator was power failure. These studies were very small, therefore they were underpowered. They were likely to have a very high false negative rate, but also underpowered means very high false positive rate, and with a little bit of bias, it also results in tremendous false positive rate and exaggerated effects, even when the discoveries reflect genuine effects and genuine associations. A few months ago, we looked in depth at about 30,000 papers in 3 large fields in medicine psychology, cognitive science, neuroscience, and psychology. And again, we saw that the typical study tends to be so small that even when something is discovered, it's far more likely to be wrong than to be true. Preclinical research, the industry has done a number of empirical assessments of preclinical work because they do care about these results. These are the papers published at the best academic institutions, extremely highly cited, coming in Nature and Science and Cell. The industry wants to build on them to develop their new technologies, their new interventions, their new drugs. So if they're not correct, they're going to waste hundreds of millions of dollars for no good use. Reproducibility rates range from 0% to 25% in that field of investigation. Glenn Begley, who led the assessment on behalf of Amgen for oncology drug targets, found that only 6 of the 53 top papers could be reproduced, and his conclusion was that we have a serious problem. Most of that basic research is just wrong, and we're wasting all these resources trying to move forward with a false starting basis. Many other examples. We see similar problems with different types of technologies, with different types of measurement tools, with different types of research designs. We see similar problems across neuroscience, pharmacology, genomics, bioinformatics, stem cell biology, oncology in vitro testing, chemistry-led discovery, computational biology, pathology biomarkers, organizational psychology, observational research. The list is just partial here. It's much longer. And these fields detect these signals of problems of reproducibility, but it doesn't mean that they all face the same challenges or the same biases that cause that lack of reproducibility. A few months ago, along with Dan Fanelli and Rodrigo Costas, we published that paper in PNAS, where we took meta-analysis from all studies, from all fields of science, across 22 major fields of science, including about 52,000 studies, and we tried to see whether there's hints of biases across these different scientific domains. We could probe for evidence for 17 different types of biases across fields that are as different as social science versus economics versus physics versus medicine versus genetics versus computer science. Most of the biases, like, for example, small studies tend to get more into trouble compared to larger studies, were shown to be prevalent across all fields. But their strength, their magnitude, their persistence was quite variable across different fields. So, for example, the gradient between small and larger studies was far more prominent in social sciences, still prominent in life sciences, not very prominent in physical sciences. Gray literature bias, conversely, physical sciences, if anything, had a trend for a stronger point estimate. Decline effect, meaning that the early studies suggest very strong effects versus smaller effects in subsequent studies. Again, some discrepancy across different fields. US bias, meaning that investigators in the US, they get more funding, but they are also under more stress and more competition, which means that they need to generate even more extravagant results in either direction. Again, some fields have more of that compared to others, and so forth. So we know many of the problems. We don't know all of them, but we know many of the problems, and we know that many of those are somehow interwoven with the way that science is rewarded, incentivized, and eventually disseminated to other scientists and to the public. Can we fix these problems by tuning our research practices and tuning also our rewards or incentives towards what would be more reproducible research? We do have also many solutions because, as I said, all these different fields have seen some of these problems for some time, and it's not that we're just staring at them. Each one of us and scientific communities think of ways to overcome them, and we have many successful examples where research practices have been modified in a way that the process have become more efficient and more credible and more open and more reproducible. The question is, can we transplant these successes, these stories where things seem to work, to other fields as well that maybe have not used them and also have the propensity to be able to adapt them? There's also many other suggestions for interventions in the way that we do research that may be interesting, but no one has ever tested them out. And there's always a risk that if we adopt something that doesn't have empirical evidence to support it, we may do more harm than good. So I would argue these speculative ideas need to be tested at least in pilot studies and ideally in experimental studies to see that they do make a positive difference. Where should we intervene? Research has a continuum from thinking about it, thinking a research agenda, and designing the study, conducting a study, analyzing the data, and then reporting the results. There's problems along that continuum, and openness can really affect any of these steps, and we can have open science or non-open science in all of these steps. Much of the time we're intervening pretty late. Most of the efforts are trying to fix science when it is done. So open access journals, great idea, make these results available to everyone. But if the results are wrong, making them available to everyone, just disseminating wrong results to everyone, is that better than disseminating wrong results to fewer people? I'm not really so sure about it. Or follow reporting standards, a checklist of 30 things that you need to do and report when you report on a clinical trial, on a meta-analysis, on an epidemiological study. Very useful, but again, if I have done a horrible study and out of these 30 items, 10 are missing and another 15 are completely ridiculous the way that I did it, and I have to confess, if I follow really that guidance, that on 15 out of 30 things that I could do, I did them completely wrong. You enter into some normative responses that people will try to cut corner, give a little bit of a vague response about what exactly they did. So intervening early makes more sense. At the same time, you also have to consider what is the cost, what are the resources needed. Do we really need to have everything being perfect? Is every single piece of science like a work of art that we need to preserve and not have the slightest dent in the frame because it's a Da Vinci or a Botticelli? Or is it that a lot of science is just junk? And junk should just go away rather than try to optimize junk. So there's always a tension how much we need to invest at each stage and how much are we trying to optimize and what is really optimizable versus just to be deleted or neglected or forgotten. This is a family of interventions that I tried to summarize a couple of years ago in a paper in PLOS Medicine. There's 12 groups of research practices that may lead to more reproducible science. And they have variable support. I have mentioned already several of them, but let's take a closer look at a few more with some empirical data. Collaboration. I think that I'm preaching to the converted if I tell you that collaboration is a good thing, that team science has really improved the standards of multiple fields. Some fields have become highly reproducible while they were completely irreproducible. Genetics, for example, used to be a field where each one of us would run small studies with p-values of just a little bit less than 0.05. Selective reporting, a huge problem. Publication bias, almost nothing could be replicated. And then we joined forces, we created very large consortia, we had standardized methods, standardized analysis. 3 different teams would run the same analysis independently, compare notes, everything would be open to everyone to see and to repeat and check and verify. Much more efficient at lesser cost. Also technology massively improved, so that made our life easier. So now, replication is a sine qua non, large-scale consortia is taken for granted. Everybody will do that if they want to publish something seriously in a major journal. In other fields, that paradigm may be equally applicable. In some others, it may still have some obstacles to overcome. Who's going to replicate and when? Is it going to be the same people? So within consortia, who are the originators and who are the replicators? Is it going to be people from the same school believing the same theories? Is it going to be people from different schools? That might be even more exciting. If they do get the same result, that's even more convincing perhaps. Do we need some completely independent replication? There's a lot of empirical evidence that independent validations tend to yield more conservative estimates compared to validations that are independent as far as the data are concerned, but they're done by the same teams or by, let's say, inbred teams of investigators. And how many problems eventually need to be so open that anyone from the community could try to perform part of them, either in the original frame or as part of the replication. So lots of mathematics problems currently can be distributed to tens of thousands of computers, and each one of us may do a little bit of that problem and get some result, and then compare notes or bring these data together. How much do we need of all of these options, and how do we apply them is an open question, and it has to be answered on a case-by-case basis within each field. Registration is also promoting reproducibility because it poses some requirement that the idea, the hypothesis, the protocol is pre-specified. And others can see that was my intention, that's what I wanted to do. However, much research cannot really be pre-specified. It's entirely exploratory, and I would argue that what we need in that case is someone to acknowledge that this is what I have been doing. I have been doing entirely exploratory research. This is fine. Now I have found something, it needs to be replicated, it needs to be validated before we can take it really seriously, but that's exactly what has happened. And I'm perfectly fine if 70% of research is exploratory. Maybe that's the right percentage, maybe even more, but it needs to be acknowledged as such, and currently this is not acknowledged. Everyone is struggling to create a narrative, a logical narrative that everything seems to be explainable and falling into place post hoc, and this is very, very dangerous. Then you have other levels beyond level 0, the ground floor. You have level 1 registration of a data set, level 2 registration of a protocol, level 3 registration of the analysis plan, which is different than a protocol because a protocol can have zillions of different analysis plans looking at the same types of outcomes. Level 4, both the analysis plan and the raw data. And here, raw data could mean 20 different things, depending on whether we're talking the very raw data, all the way to processed, cleaned, processed, squared, selected, streamlined, corrected, distributed. You can have a vast gradient of what raw data means. And finally, open live streaming, where everything is shared with the community before it is done, and with feedback in real time from the community on how it should be done. This is one example of a registered report. 54 journals, if I'm not wrong, as of today, have endorsed this policy. So practically, the authors can submit their paper fully written without the exact numbers in the results. So it's a full paper, not just the intention, the objectives, the methods, but also the results. These are going to be the 3 tables and the 2 figures that I'm planning to collect information and populate. And then this is reviewed. Then the study is done. The numbers are populating the figures and the tables. There's some discussion and the paper gets published. Is that the way to go? This is a very strict way of registration and openness. We're currently looking at its success, and we have several examples where it has worked, but we also have several examples where it hasn't worked, and where really the degrees of freedom, despite this seeming high level and intense registration, the degrees of freedom on what exactly can be done are still very, very large. And therefore, the same registered report could be manipulated in much the same way as any analysis that hasn't been registered at all. Data sharing is an idea that has been floating around for many decades. And several years ago, when we did a survey of the top 50 journals across all science in terms of impact factor, we found out that most of them had policies in place for sharing data, for sharing protocols, for sharing materials, for sharing software, and most of those actually made that a prerequisite for publication of the work, that the authors should share that or be willing to give them away as soon as they're asked. But if you look more carefully in the last column, there's lots of zeros, and this is how many out of 10 papers that we screened from each one of these journals actually adhered to these policies. So sharing sounds nice, but it's not really happening as often as we want it to happen. And this doesn't mean that someone specific is to blame, that someone is not fulfilling their duty. I think it's a bigger problem with multiple stakeholders to decide who exactly should share and when and how. Preparing data sets, preparing publishable data sets that can be meaningfully used, and also publishable versions of other materials can take a lot of effort. It can take resources. One has to find ways to decide what is the optimal timing for that sharing. Who would be eligible for that? Is it going to be the entire community? Is there going to be some gatekeeper mechanism? How do we protect from rogue analysis that just try to get things wrong, just to create confusion and to put investigators into shame, or whatever people may worry about? How do you allocate credit to people who share, and who gets credit for things that are generated out of the sharing process? So there are answers to these questions, and some fields have found better answers compared to others. And this is why some fields have promoted sharing to a much larger extent compared to others that still see databases and other materials as private gold mines not to be communicated with others. This is a survey that we did recently where we took 500 random papers from PubMed, so this is the entire biomedical literature roughly, and half of them had primary data. None of them actually shared all their data. One of them shared a very detailed protocol, and that was a separate paper that had been published for the protocol per se. So across the board, at least until 2014, which is the end date of our survey, there was little sharing happening, even though the best journals were talking more about it, and maybe they were doing a little bit more. and even though there are some fields that have processes in place like genomic epidemiology, most fields would not share data and protocols. There are exceptions. So for example, for clinical trials, we're seeing a vastly, rapidly changing environment. In the last 3 years, at least 13 companies have agreed to share all their old randomized clinical trials worth of data. So we have the option of tapping into something like 14,000 randomized clinical trials worth of data, not entirely open to anyone. You need to ask for that, and you need to get through some approval process, but it's not so tough. Many other organizations and funders are also sharing all their clinical trials, particularly NIH. And some journals in the last 2 years have also moved forward to say, it's not that you need to tell us that you're willing to do it, you need to do it. It's a must. It's not just, it would be a good idea, and if they ask, yes, we may, yeah, maybe, it needs to be done. So we went ahead and tried to see whether PLOS Medicine and BMJ, that have this most open policy for sharing information from randomized trials, actually this is happening. We took every single trial that they have published after the initiation of this policy, and we went to the investigators and said, we want to get the data, we will reanalyze your data. Just leave it to us, no cost, we'll do it for free. 46% of them did send their data. Is that half empty, half full? I mean, these are like the creme de la creme, the most open of all. About 50% did send their data. The good news is that when we reanalyzed the data, we did get the same result. We found 2 errors, but both of these errors were not really such that would invalidate the conclusions of the study. So at least in the sample of the most open journals and the most sharing and the most willing authors, we could get the same results. It doesn't mean that we would get the same results if we got a random sample of a data set from any study published, but at least we have a mechanism that seems to be generating reproducible science. Another field of great activity is at the level of improving the reproducibility of computational methods. As I mentioned up front, we need to have access to software, to scripts, to code, to be able to see whether, combined with the data, we can get what the original result was, and also use these resources for other experiments, for other studies, rather than just have them hidden or disappeared and no one having access to them. A few months ago, we published a set of recommendations in Science where we argued that we don't want to be utopians, so we realized that there's levels of endorsement of these recommendations, and the lowest level of endorsement for a journal would mean that someone, could be the editor, it could be an editorial assistant, if they see a link that there's a database here, should just click on it and see that there is a database and that there is some software and that it does run. Now, if it runs correctly, that's a higher level, and if it does get the same results as they have been claimed, that's yet another level. And if you want to go through the whole range of what I would call forensic bioinformatics or forensic informatics, of rerunning everything from scratch, obviously that's something that most reviewers would not be prepared to do, with some exceptions in some fields. But we have to think when and how and who might need to invest resources to do that extra check, to a larger depth of checking the reproducibility. And obviously this needs to be probably done on a select sample of studies. Better statistics and methods can also take us a long way. There's a lot of empirical evidence that most of our scientific workforce is scientifically illiterate and innumerate. I don't say that to blame anyone. I'm sure that I'm also illiterate and innumerate in many studies that I have done, that I was not even aware that there is a better study, but a design and better method. But the truth is that we are trying to be competitive and trying to master the subject matter of our domain rather than keep up with methods. And methods are evolving very quickly, and methods also have lots of caveats. So fixing that problem would need reshifting the entire focus of scientific education. How do we build scientists? How does one become a scientist? Currently, it's like a recipe. You need to catch up with the latest measurement tool. The right recipe would be you need to catch up with methods and make sure that you understand how to use them and how not to misuse them, and catch up with the new measurement tool in terms of the methods that are needed for running that measurement tool effectively and without biases. We know what are the best study designs. Yes, there's some ambivalence that there's 2 or 3 or 5 options in some cases, but most of the time we're not using the best study designs. We know that there are some things that are standard that should be done, like randomization and blinding of investigators in animal experiments, but still it is not done other than maybe 10 to 20% of the time, even though experimenter bias is known since the 1950s. So we know how to fix that, but very often we see examples like this one, where fMRI studies, about 30,000 of them, that had been studying spatial extent analysis, they were using some parametric methods that, looking more carefully, one realizes that a p-value of 0.04 actually is a p-value of 0.8, more or less. So these 30,000 studies could have had misleading results. Not all of them were misleading, but probably several thousands eventually had misleading results just because a statistical technique was massively misapplied for years and years, and nobody really said that's not the way to do it. A few days ago, we published a paper in Nature Human Behavior where we argued that for fields that don't use methods other than null hypothesis significance testing and are using NHST and p-values of 0.05 as a threshold of success, this is not a good idea. How to fix that bad idea? There's a zillion ways to do that. But at least we said we can have a quick and dirty fix for now until we agree on what is the best solution and shift the threshold of statistical significance from 0.05 to 0.005. That would save about 30% of the misleading claims. It's a very quick and dirty fix. I'm not telling anyone that this is the final solution, but we are flooding with irreproducible results, and I think that this at least will give some higher level of skepticism for some of those reproducible results, because in a Bayesian framework, we shift from a base factor of 3 to a base factor of 14 to 26, depending on how you want to calculate it by adding that extra 0. We can go even further. We can get rid of null hypothesis significance testing in large scale, and along with Dennis Sux, we argue that about 80% of the time, when we use NHST, we should have used something else. It's a very long paper, but in brief, if I try to think what are the research projects that I'm interested in working on currently, and these are some, developing a prognostic score for cardiovascular disease, assessing a diagnostic test for depression, evaluating medical treatments for different diseases in randomized trials, mining electronic health records or big data from metabolomics. Or here's a question that some co-investigator asked me, assessing if women athletes with high natural testosterone should be excluded from the Olympics. For all of these questions, null hypothesis significance testing is not the way to go. It makes no sense. The null hypothesis is not really what we're interested in. So we have to align statistical methods with what we want to answer. Institutions can also help. They can promote what I call continuous methodological education, or CME. Make sure that researchers in institutions are kept up to date with advances in methodology, study design, and also there's mechanisms in place to not allow highly suboptimal research to move forward. For some solutions, we just need to defer to modeling. It's not easy to study them experimentally. There's lots of approaches from economics, game theory, simulation studies, or mixtures of simulations plus experiments that could inform us about what it would mean to introduce a research practice versus a different research practice. And finally, we need more evidence. We need more research on research to understand how to make science more open and more reproducible. Because as I said, some of these ideas may seem interesting, but actually they may not work. So there's lots of initiatives around the world that try to improve how to perform research, how to communicate research, how to verify research, how to evaluate research, and how to reward research. And this whole field of meta-research is growing at a geometric pace, These are just a few such entities that we have cataloged. There's currently about 500 entities that work on these areas as one of their top priorities or goals or aims or objectives, and the number is growing very fast. One of them is our Meta Research Innovation Center at Stanford that is trying to create a connector hub for such activities. To close, all of these changes depend on rewards and incentives. They will not happen unless we reward scientists, we reward researchers for doing the right thing. And currently, we reward researchers mostly for producing, and productivity is great. But we also need to find ways to reward quality of scientific work, reproducibility of scientific work, sharing of data and other resources, and translational impact of research for scientists who perform applied investigation. So you have a PQRST, which runs like an electrocardiogram, and we need to focus on more than just the P wave. Do we need evolution or do we need revolution? Many of these changes will happen slowly, others need to be happening urgently, and maybe we do need some revolution in many fields that are lagging behind. This is what we propose in that manifesto for reproducible research that we published recently, and you can read it along with a number of solutions being proposed that would involve different stakeholders, scientists, journals, funders, institutions, professional societies, people working in informatics science and beyond. We need to align the interests of all these people who want to publish, who want to get funding, who want to translate, and who want to make profit, and that's not necessarily very easy. To close, reproducibility has different meanings across different scientific fields. Eventually, all of them aim at enhancing our trust in scientific findings. There are many possible interventions that may improve the efficiency of research practices and the reproducibility of the scientific literature. Empirical meta-research would be useful not only to assess the prevalence of these problems of reproducibility, but also to assess the effectiveness and the potential harms of intervention that try to make research more reproducible. I will close with special thanks to some of my colleagues who have helped in some of the empirical work that I showed you today, and thank you for your patience.